We're doing an intro to machine learning in here. If you haven't met me, my name's Jesse. I'd like to say hi to you afterwards. And I work at a really cool company called Planning Center, and we do something where we have what we call free weeks. We do this a few different times throughout the year, and it's basically a time where we can just sort of pick our own little project that we think might be valuable to the company. We can kind of just experiment and try out different things. And I had a couple of ideas that I thought machine learning could really help us out for. So in our last free week, I was taking some time, and I decided I'm going to dive into this. I'm going to really figure out how to do some machine learning, and really going to transform our company with some machine learning. So I looked around, and everyone kind of recommended the same course. There's this course, I think it's on Coursera by Andrew Ng, and it's like the de facto, if you want to learn machine learning, watch this course. So I was like, sweet, this is great. Everyone's recommending the same thing. I'm going to check it out. And so I was watching it, and it's free, which is awesome. And I got about an hour into the course, and it looked like this. And I realized I have no idea what any of this means. Like, he was explaining it as he wrote it all up there, but I just didn't get it at all. And I realized it's because of a fateful decision I made quite a long time ago. In the late 90s, I was presented a choice, and that choice was calculus or racket sports. And I chose racket sports. And I had a great time playing racket sports with some of my buddies in high school, but unfortunately, it's not helping me out with my machine learning. And pretty much any machine learning course you look at, they're using calculus to teach you how machine learning works. And that was a big problem for me because I don't know calculus. I never took the time. I'm pretty good at racquetball, but I'm not very good at calculus. But really, math is just a language. It happens to be one that is really good for teaching machine learning because you're dealing a lot with formulas and numbers. And it's great for that. But if you don't know it, we know another language that is pretty good at transforming things. So we're going to use Elixir to kind of learn some machine learning today. And before we dive into that, we need to kind of define, like, what is learning? Like, what is the machine going to do? And one definition is to acquire knowledge or skill through study, instruction, or experience. And if we reduce this even more, we can kind of take it to a more primitive level. And really, it's all about experience. Like, you can't study something that someone else hasn't experienced, and you can't teach if you haven't if no one's gone through that experience. So what we really need to do is we need our machines to be able to have experience and learn from it. And the way that they learn from the experience is by reducing error. And this isn't just with machines. Like, you think about a child learning how to ride a bike. When they first start, they're falling over all the time. But over time, as they continue to have more and more experience riding that bike, they reduce their error rate. And eventually, the error rate gets low enough where they don't crash all the time anymore. And it gets low enough that you don't even say, like, oh, they're learning to ride the bike. You just say, oh, they learned to ride the bike. They know how to ride the bike. And that doesn't mean they're never going to have an error again. It just means their error rate lowered enough that they pretty much know how to ride a bike now. So that's sort of our basis of what learning is and how we're going to teach our machine to have experience and reduce error to learn from it. So I'm a pretty big movie buff. I used to see so many movies, tons of movies. Then I got married and had 3 kids, and I don't get to see nearly as many movies anymore, which is a bummer. So one way that I could use machine learning is I can build something that's going to help recommend movies that are custom to me that I'm going to like. And so I happen to know that I recently saw the new Star Wars movie, and I was a huge fan of it. And so I know that this is a movie that I do like. So maybe I can take that data and teach the machine to recommend other movies that I will also like. So to do that, we need to start with some data. And so we'll just take the Rotten Tomatoes critic rating of 90%. And we're going to use that as kind of our basis to learn how to recommend movies that I'm going to like. So we'll take our 90 and we'll throw it in what we call a neuron. And this is basically just something that stores that value. You can kind of think of it like a process where the state is just this number 90. It's just hanging on to that number. So that is going to be our input value. and we're going to pass it to another neuron, and this is called our output neuron. And obviously, not much is happening here. It's a pretty simple little pass here. And if we were to write it as a function, we get a very simple function where it takes an input and it returns that exact same input. But if we do it as that, like piping the value, you can kind of see that it models what we're doing. Like, okay, we've got our input of 90. We're going to pipe it through this simple function, and it's going to return the result, which is also 90. So that's pretty simple there. We're going to make it a little more interesting, and we're going to add a weight. So what this is going to do is it's going to take our input, and we're going to multiply it by the weight, and we're going to get an output of 0.9. And this is great, because what we want this network to do eventually is be able to, we give it a movie, and it outputs a number between 0 and 1, 1 being that, yes, I'm going to love this movie, I should go see it, or 0, I'm not. And so it's kind of this probability scale between 0 and 1. So right now we've got it giving a 0.9, which is pretty close because we know already that I do like this movie. So that's a pretty decent result. And if we do this in a function, it's pretty basic. We take an input and a weight, multiply them together. And again, piping it through kind of gives us that model of where we're seeing our input, our 90, we're passing it through and applying that weight, and then getting our return, our output at the end there. And so now that we've done this, we have our extremely simple neural network here. We're going to add a little bit more interest to it, and we're going to have a few different outputs. So we're still just going to take our 90 input value, and instead of just figuring out if this is a recommended movie, we're also going to say, well, let's predict what we think the box office is going to do for this movie. And maybe we want to predict what the Oscar odds are for this movie. So to do that, since we only have our single input with the 90, we're just going to use some different weights to get those outputs. So we'll just say arbitrarily kind of 500,000 is our weight to give us, a box office number in the millions, and 0.002 is going to give us our Oscar odds. So we do that, and all we're really doing here is 3 copies of our simple network, because we have our single input, and we're going to pass it through a weight. So we're just doing it 3 different times with the same input for all 3 of them. And if we used a function for this, it's pretty basic. We take our input and our list of weights, and we map through the list of weights, and we just multiply it by that input. So if we see it, again, take the 90, pipe it through that function that has our weights, and then outputs a list of our 3 different output values. So go ahead and throw that back on here. And this is cool. We're like predicting some stuff. It's probably not all that accurate. And part of the reason it's not going to be very accurate is we only have that single input value of 90, which is probably going to be pretty limited for what we need. So we're going to take that and we're going to see what other data we can use to be able to predict movies that I will like and box office, et cetera. So in addition to the 90% that the Rotten Tomatoes gives you, it also gives you an audience rating, which for this movie is pretty interesting because they're quite diverse. There's quite a change between the 2 ratings, so there's probably some interesting data we can get by comparing those 2. But I can look at this and I'm like, well, shoot, I know that I saw this movie and I know that it's a movie that I like, and so I don't want those to be the only input. What is a value that because I know that I like the movie, what's a value that I could have put in there that would have helped me to know that before having seen it? And so one thing about this movie is maybe the director. The director of the movie, Rian Johnson, happens to be a director I really like. He had the movie Looper, and I was a huge fan of that movie. And so if the network knew my preferences and knew that this movie was directed by Rian Johnson, that could help it recommend and let me know that I'm probably going to like the movie. But it's hard you can't really apply a weight to the name Rian Johnson. Like, that's not going to work. So another way we could do this is make Rian Johnson like a Boolean. So we can basically say, did Rian Johnson direct this movie, yes or no? And if we wanted to do it for a bunch of directors, we could have an input for every single director. 0 means they didn't direct it. 1 means they did. And another way you could look at this is just like, hey, how many Rian Johnsons directed this movie? Oh, 1, perfect. So now we've got our 3 inputs. We're going to throw that into this multiple input with a single output network. And the way we do that is we do the same idea before where we have our simple network where we're taking our number, passing it through a weight, and getting our result with 3 different inputs. So we're going to do it here without the weight real quick. And all we do is take our results on the right, and we just add them together. We sum them up, and then that gives us like our final value of 139. And if we put the weights in there, we can see like, okay, take the 90, apply the 0.005, same with the next, get the results of those, sum those together, and then we get our output of 0.77. And the way we would do this in a function, because we have our 3 inputs and we have 3 weights. So we're going to take a list of each of those, and then we'll just zip it together and multiply each input by each weight. And then that's going to return, pipe it through, and then it's going to return our values, 0.45, 0.12, and 0.2. And one last thing we want to do, now that we have those values, is we just added sum to our function. So we make sure we add them up, and we get our final output of just 0.77. So even though we kind of have like all these things on the right, all of that is actually happening inside of a single output neuron. So it really just looks like this, but it's taking the different weights, different inputs, multiplying them together, and then summing it into a single value. And again, we can do that for multiple outputs. So here we have a different set of weights. We have the same inputs, but now we have 3 more weights, so a total of 6, and we get our output of 88 million. And we do it again for 0.49, and you can see here one of the weights is negative, so they don't have to be a positive number. It can take this data and say, like, actually, the audience rating doesn't help Oscar odds. It does the opposite. We want that to bring the number down. So now we have a total of, we have our 3 inputs, and then we have 3 different sets of 3 weights, one for each output. And so to put that through, we take our previous mult inputs function, and we're just going to map our weights, our list of 3 different lists of weights. We put that down here so you can see your weights. You've got your 3 different chunks. Then you're going to map through each one of those, and then zip it together and multiply by the inputs, and get the output values 0.77, 88 million, 0.49. And so now we see this here, and we have kind of a little bit more of what a network model kind of looks like. And we can see like, okay, so we've got kind of all these values, like each one of the inputs is passing to all the outputs, and it's applying the weights. The one problem with this kind of model is it's hard to see like what the weights are, and so you can kind of just visualize it. If we just change like the width of the different lines, you can kind of visually see which inputs are more important to which output. And then we have the one negative output for the 4.8. We just put that orange so it's obvious what's happening there. All right, so we finally got it. So we have a really basic neural network where we can do our 3 inputs and our 3 outputs, and this is pretty cool. But we can do something to make this a lot more powerful, and that's something called hidden layers. So hidden layers is, if you look at, it's basically just adding another kind of output layer halfway between the two. So you start out, you take your inputs, and we're just going to look at the first neuron of the hidden layer. It's going to take the inputs, apply the weights, get the result, and what this is kind of doing is it's looking for patterns that's going to help it figure out our final output. So like maybe like when we're trying to figure out the output value of what is, what's the box office going to be, maybe this pattern can figure out that, oh, this is like a blockbuster kind of movie based on the director, the marketing budget, or some other sort of input value. It can figure out the pattern of what kind of movie this is. Or maybe it can figure out like, oh, the audience rating is low, but the critic rating is really high. And so maybe this is like an Oscar bait kind of movie. So we want to be able to figure this pattern out, and then we can push that weight to our Oscar output, Oscar odds output, to make sure it knows like, oh, this is more likely to win an Oscar based on the fact that we think it's an Oscar bait type of movie. Or maybe the opposite. Maybe the audience rating is really high and the critic rating is really low. And like, oh, this is probably a cult classic. So maybe we can use that to figure out like if that's more or less recommended for me or whatever. And the same thing you can kind of use this to figure out different genres based on directors or actors that might be in this movie. But the important thing to know about hidden layers is we don't actually know what they're doing. We can kind of conceptualize, like think about what it might be doing. Like it might be finding this kind of pattern, or that kind of pattern, but it's really kind of more of a black box. We don't actually get to know what's going on inside of the neural network. It's kind of, it will be figuring out the best way to come up with these patterns to give it the right output. So anyway, so once it does that and it comes up with its output value here, then we go to kind of the next layer to get our final outputs. And this value in the hidden layer now becomes just an input for that side. So basically what our neural network that we had before, we're basically just taking that and then taking the output values of that and then passing it on to another layer. So we're just sort of stacking that network, other than the fact that we don't know what the hidden layer is going to be doing in the middle. But if we look at our basic functions for our inputs, for our hidden layer, it's going to take our inputs and it's going to apply some weights to it, and then it's just going to sum the result, just like our outputs did. But there's actually a problem that this introduces that maybe isn't super obvious, and it's the difference between having something that's linear and nonlinear. And the problem with what we have right now, we take this, we'll have this version with multiple hidden layers, and this is actually linear, which means that basically, well, here, we'll do like an example. If you took an input value of 90, and then you came up with this kind of great formula to come up with your ultimate result, maybe we're going to multiply it by 0.05 and 0.25 and 120. Like, this is great. It looks like a kind of a complicated formula. But really, if you just multiply these three together, like, that's the same exact formula. Like, because it's linear, it's going to give you the same result, and you don't need to multiply it multiple times. And the same thing is true with this network right here. Whatever output that's coming up with, we could come up with the same output without any of the hidden layers. So we're going to need to do something with our hidden layers to give them kind of that magic that's going to let them add more and make it nonlinear. So we're going to go to this function we got where we have our inputs, where we apply the weights to it and then sum it up. And then we're going to add what's called an activation function. And these are really simple functions, and there's a lot of different ways that you can do this. Three of the common ones are the ReLU function, sigmoid, and the tanh. And ReLU, basically all it's doing is you're feeding in a number, and if the number is negative, it changes it to 0. If it's positive, it just passes it through. So 32 becomes 32, negative 5 becomes 0. And that is all that the ReLU function does. The sigmoid function takes any number and crushes it down to in between the values 0 and 1. So if you put in like the number like 3, then it might be 0.7 or something like that. If you put in the number 10,000, it's probably going to be like 0.998 or whatever. And you put in the number like negative 500, it might be like 0.1. So it's kind of like crushing that number into that tiny scale between 0 and 1. And tanh is similar, but the scale is between negative 1 and 1. So it's like twice as wide, and that kind of gives you like a nice, 0 is like a nice dividing line of, is this a positive or is it a negative value? But we're just going to use ReLU. The nice thing with pattern matching is it's really easy to define. It's like, hey, if it's less than 0, return 0. Otherwise, pass the number through. So now our hidden layers are going to, our hidden layer neurons are going to be applying this function to the inputs it gets. It's going to apply the weights to it, sum it up, and then it's going to go ahead and run the ReLU function. And all this is going to do is, if it's negative, it's going to kill it, make it just 0. And the result of this in our network, if we throw in some weights in here, we'll take a movie and pass it through, and you see some of the neurons are orange, and that's meaning that it got a negative value. It summed up the results, and the value is negative. So it is now actually going to turn off. Technically, it's still passing its value through, but because the value is 0, whatever the weight is doesn't matter, because it's still going to equal 0, and it's just going to disappear when it's summed up in the next neuron. And so you might look at this and think, like, well, this seems dumb, because why is this neuron here if it's not even passing value through? And the thing you need to consider is these neurons are turning off based on each set of input that goes in. So maybe for Star Wars, we put the Star Wars movie through our network, and it hits here, and that one turns off. But maybe maybe we put in like an Adam Sandler movie, and that neuron's firing, because that's looking for some pattern that an Adam Sandler movie has and Star Wars doesn't. So these are turning off and on based on what your inputs are giving you as they apply the different weights. All right, and there is one more thing. We're not going to go over it, but I just want to mention it. We can also, before running our ReLU function, we can apply a bias. And this is basically something like, maybe this neuron doesn't want to pass on any value unless the value is more than 20. And so the bias is just going to subtract 20 from our sum. So if our sum is 25, we get the value of 5, and that'll go ahead and pass 5 through. But if our sum is 15, that's going to subtract 20, we get negative 5, and the ReLU wipes that out with the 0. Yeah, all right, so this is cool. But we're not actually learning anything. Like, all we're doing is, pushing all this data through and getting some predictions. And maybe more importantly, like, the weights seem really important, and where do they come from? Clearly, we need to figure out how to come up with the weights, because that is basically doing all the work. So the way we come up with all of our different weights is really easy. We just randomize it. We take every weight, and every weight gets a completely random number. And so for this, say we do a number between -1 and 1. And it just sort of throws, so each weight has just like a starting value that's random. And then that's what we're going to use to start our network. So we'll take this with our random weights in here, and then we're going to go ahead and grab our movie that we know we like thumbs up. We want the result of this to be 1.0, because that means, yes, this is a movie I like. So we're going to mark that as our target. Our target for this is 1.0. We're going to take our different input data, throw it in the neurons, and then we're just going to run it all the way through, and it's going to apply all of our random weights, and who knows what we're going to end up with, because it's just random. Like right now, there's no intelligence in here, which, maybe that's kind of like a kid first trying to learn a bike. They don't really know what they're doing, which is why they fall over nearly immediately. At least I did. All right, so we're going to pass it through, and so we take our 90 and our 40 and our 1, and it passes through that first layer. Those neurons then sum it up, run the ReLU function to make sure it's not negative, and then pass its results on to the next level. Pass it through again and again, and then we get our result, and our result, we get a 0.6, which, it's not great, but it's on the right side of the scale, so that's pretty cool, since all we started with was our random numbers. So we're going to go ahead and take note of that. So that's our prediction, 0.6, and our target was 1.0. So we're going to go ahead and write that down, like, all right, well, this is what the network did for that movie. Let's go ahead and pass another movie through. We want to try and get like the other end of the spectrum. So let's find a movie that I know I didn't like. And so there's a director that's a little bit divisive. His name is M. Night Shyamalan, and I happen to be a huge fan of M. Night Shyamalan. I kind of used to call myself kind of an apologist for him. A lot of people like Sixth Sense, but I loved like Unbreakable and Signs. Sixth Sense was good too. I liked The Village, which a lot of people. I even liked Lady in the Water, and that's when a lot of people hated that movie. I loved Lady in the Water. But then he released another movie. It's called The Happening, and going to the theater to see The Happening was one of the worst movie experiences of my life, because I was so excited. Like, I thought the premise sounded really cool, and M. Night could do no wrong. I was so excited to see this movie, and it was a huge bust. I just hated this movie. And I really want to make sure that this machine that we're training here is going to make sure I never have an experience like that again. So we're going to go ahead and feed in The Happening here. So our target is a big fat 0. We're going to take our input values. Critics, also not a fan, 18%. Audience gave it 24, which I think is crazy, but some people apparently liked it. And we had 0 Rian Johnsons directed this movie. So we're going to go ahead and pass those through. And again, these are the same weights. We're not randomizing them again. We randomized them once when we set up the network, and now we're not touching them. So these are the exact same weights that gave us the result for Star Wars. And with this movie, we get a result of 0.4, which is like, still, it's not that good. Like, I want that to definitely be a 0. But it is on the right side of things. At least it's telling us that we're going to like Star Wars maybe a little bit more than The Happening, which is just happenstance, because these are random values. So let's go ahead and take a look at those and figure out what can we learn from this data. So we can take our prediction and subtract the target, and that's going to give us a number that kind of tells us how much we missed by what we wanted our result to be. So we see that Star Wars kind of undershot by 0.4, and The Happening overshot by 0.4. But the problem with this result is if we are going to look at this and say, okay, so what was our average error here? Well, it's 0, and that's not right. It missed both times by quite a bit. So we don't want this to be our actual error rate. We want our error rate to be a positive number so that we can see it going down. We want our error to be a positive number that we can push towards 0. So instead of calling this our error, we're just going to call this our delta. And delta just means like a number that represents like a distance between two other numbers. So our delta here just represents the distance between what the machine predicted and what the actual target was. And to come up with an error rate, we're going to just take our delta and we're going to square it. And what this does, a couple of things. One, it gives us all positive numbers, which is what we want because we want our error to be positive so we can reduce it. And also, if we have a large error, it kind of magnifies it. And really, if you're thinking about like a recommendation engine, that's what we want. Like something that's within like 0.1 of the real answer, that's pretty close. We don't care nearly as much about that as the one that's completely off. Like a 1.0, when we wanted a 0, we definitely want to fix that error. So that one, by squaring our delta, it really kind of grows that error and makes it stand out as something we need to fix. And again, the nice thing with the positive numbers, we average our error together and we get an actual good, useful average there. And another way to think about this is if you think of like a bullseye. So we threw the two movies at our targets, and one of them overshot by 0.4, and the other one undershot by 0.4. But they both missed by the same amount. If you took a ruler and measured the distance between where it landed and the target, you're going to get the same amount of distance for both of them. So it makes sense that we're kind of squashing that delta into getting an error that is equivalent. So now that we know that we have an error, how can we reduce our error rate? We've got all these random numbers in here, these random weights. How are we going to make it do better? And one thing we could do is we could just grab one of these weights, and we can kind of wiggle it around, like, well, what happens if we raise this? What happens if we lower it? Like, oh, lowering it helped, lower it more. But we're really just sort of like guessing, and we have clearly a whole lot more weights that need to be adjusted. It sounds like kind of a nightmare to just be kind of manually adjusting all those. So luckily, there's this cool thing that's called gradient descent, and I'm just going to do kind of a quick basic overview of it. There's a lot more to this idea, but the basic idea, if you were to chart out, like say our target is 1.0, and if we hit 1.0, we know that our error rate is 0 because we hit our target. So if we were to randomize our weights and throw a movie through and just throw that dot on the map, we see that, okay, we overshot the target. We're at like 1.2 or whatever the scale is, and then that shows us like an error rate. And we could randomize the weights again and throw another one through, and then we get this one. Oh, this is closer to the target, so obviously the error rate's lower. And we could keep doing this, and we kind of throw a bunch of different targets, and a pattern starts to jump out. And you can see that this actually kind of creates like this bowl shape. Like the further away from your target you get, it kind of, because we're squaring our delta, it's exponentially getting further, like our error rate starts to skyrocket as you get further away. And what you see here is basically we kind of have the idea of like a bowl, and we want we have our prediction right here, and we want it to go down the bowl. We want it to get to the bottom and hit our target of our 1.0 with the 0 error rate. And our delta actually tells us which direction to go. Because where we are right here, we know that we undershot the target, and that means that our delta is going to be negative. And so we can use the fact that our delta is negative and push it in the positive direction. So we're gonna go ahead and do that, and then that'll push it over here. And we're like, okay, so we made a new guess. We're closer to the target, but we still missed. This time we overshot, so our error rate's lower, which is great. And now we can see that we overshot. Our delta is a positive number, so we need to reverse. We need to go back the other way. And you can do it kind of again and again until you land kind of pretty close down until you get that kind of acceptable error rate. So let's say we're going to go to our simple network again. Let's say we've just got 2 neurons. We've got our input value of 0.8, and we're going to apply this random weight of 0.5, and our output is 0.4. And we're going to say that our target was 1.0. So we've got our little formulas that we figured out, our really simple formulas we figured out before. So we can figure out the delta by taking our prediction, 0.4, and subtracting the target. So we get our negative 0.6 is our delta. And to get our error rate, we just square that. So we take the delta times the delta, we get 0.36. And now that we know this, we want to be able to use gradient descent, and we want to nudge our weight in some direction so that it lowers the error rate and gets us a better prediction. So we're going to take our delta, our negative 0.6, and we're going to multiply that by the input. And now this may seem kind of arbitrary, like why are we multiplying it by the input? Like what's the point of that? And this isn't the only way that you can do this. There are a lot of other complicated formulas that you can use to come up with your nudging value. But the nice thing that this gets you is a few different things. It has a thing called stopping, and what that is, well, if your input is 0, there's no reason to adjust that weight, because adjusting that weight isn't going to give you a different result when you're multiplying it by 0. So by getting our nudge value multiplied by delta times our 0, it's going to make sure we're not nudging it at all, because there's nothing to learn here. The input is 0, there's nothing there. So that's one thing that doing this delta times input to get our nudge value gives us. Another thing is negative reversal. We talked before about how with gradient descent, the negative or positive value on our delta tells us which way to nudge the weight. But if our input is negative, then that's going to push us the wrong way. Because if we undershot and our input is negative, we don't want to increase our weight. We want to decrease the weight because we want it to go up. So by multiplying it here, we don't even have to think about that. That's just that's a gimme that's automatically taken care of. And the third thing it gives you is scaling, and that's sort of suggesting the idea that the weight is adjusting relative to the input. And this can have some problems that come up, and there's several different ways to solve them. But we're just going to assume that we're not going to have those problems with our network. So we're going to skip those for now. But anyway, so we take our nudge value. We're going to take our delta, negative 0.6, multiply it by the input, and we get our result of negative 0.4. So we want to log what we've done here. So this is our first run through. We got our prediction, and we figured out kind of all this different information, our delta, the error, how much to nudge. And so we're going to go ahead and log, like, all right, well, this is our first time trying this network. We made a prediction of 0.4, and our error rate was 0.36. And then we want to figure out, like, okay, so let's try it again. Let's adjust our weight and try this network one more time. So to do that, we just take our current weight, the 0.5, and then we're going to subtract our nudge value. And remember, that's because the gradient descent, you have a negative value if you want to go up. So that's why we're doing subtraction. It's like, it seems a little weird, but the idea is like, oh, we have a negative weight, so subtracting it is going to actually add it. So 0.5 minus negative 0.48 gives us the increase in the weight of 0.98. All right, so now we're going to run the network again. Like, okay, so we've figured out an error rate, our first complete random weights. We figured out what our prediction is. Let's run it with this new adjusted weight. So we're going to run it through, and we get a new prediction, and hey, 0.78 is a lot closer than 0.4. So that's pretty cool. We see a little bit of improvement here. We're going to take that and go ahead and figure out what our delta is, and then we'll square that to get our error rate. And then we'll take our delta again, multiply it by our input, that 0.8 that's not changing. And then we get a nudge value. And now we'll go ahead and log that, like, okay, our second time through, this is our prediction, 0.784, and our error rate, a lot smaller, 0.046656. So this is great. We're moving in the right direction. And now we will take that nudge value we came up with and subtract that from the 0.98 weight. And now we get a new weight, and we're going to do that and run it again. So we'll do this a few different times. We log those results, figure out a new weight, move it up there, do it again, and log those results, new weight, log the results, new weight, log the results. And now we have just six times through this has now gotten us from an original random prediction of 0.4 to 0.9963 whatever. Like, that is looking pretty good. That is real close to the 1.0 that we're wanting. And our error rate, the same thing. You see how it exponentially just gets tiny compared to kind of our initial error rate. So this is cool, but we did this with a single weight. So this isn't going to really do it with this. Like, we've got a lot more weights here that are going to need to change for this network to be able to do anything for us. All right, so the way we're going to do this, we're going to run our we're going to take our Star Wars movie, run the data through, it's going to apply through all the weights, and then we get our results here. So we got our 0.8, and our 1.0 is our target. And with that, we can calculate our values. So we're going to figure out what our delta is. So we're going to take our prediction, subtract the target, and then we get 0.2. That's our delta. And with that, we can figure out what our error rate is. But now we actually want to, because we have 5 neurons pointing to it, we want those neurons to be able to adjust their own individual weights. So we need to pass our delta back to those neurons so that they can figure out how much to adjust their weight. Because what we're trying to figure out is we're off by negative 0.2, and we need to figure out, like, okay, which one of these neurons that are passing this data mess this up the most? Like, who is most responsible for this negative 0.2? Like, you're kind of passing the blame back. You're like get blaming and trying to see who really contributed the most to this error. And an easy way to do that, we can just take our delta and then multiply it by the weight. And that gives us kind of a scale to each weight that's coming in. And so if we do that, we'll take this top one here as an example. We'll say that the value when that summed, ran the ReLU function, whatever, so it's got 1 at the end of this network it's about to pass down, and the weight that it has is 0.5. So to figure out how much we want to change that particular weight, we're going to take our delta, the negative 0.2, and then we're going to multiply that by the weight. So we take negative 0.2, multiply it by the 0.5, and we get a delta for that previous neuron that's negative 0.1. And so now we're going to use that delta, and so think of that just sort of hovering next to the 1 there, like that's the delta for that neuron. And it's going to take that to figure out the weight. So it's going to take that delta, multiply it by its input, which is 1, so you get the same result. So our nudge value is actually the same as our delta in this case. And then you're going to subtract that from its current weight. And that's going to give us 0.6. So we can now adjust that weight to 0.6, and then we can do the same thing with all of our other ones down. All right, and so now that we have that, we need to go back to the other layer. So remember this 1 value here knows what its delta was. It has that negative 0.1, but now it's got to pass it back to all these other neurons over on the left. And so to figure this out, we're doing the same thing. We're trying to figure out, like, okay, so if its delta is negative 0.1, how much did the previous neurons contribute to this one? We do the same thing where we multiply it by the weight and pass it back. So then we end up with the new weight here. We take our weight and we subtract the nudge, which is taking that delta, the negative 0.1, multiplied by the input. All right, so we have, I skipped ahead a little bit there. We have our negative 0.1, we pass it back and figure out that previous delta by taking the delta multiplied times the weight. And then now we have the delta for our 3 neuron, which is negative 0.02. So we pass that up here, and that's, that's the one that we use to change that 0.2 weight. And all the other ones will do the same thing. Each neuron on the right will be passing back a delta, and it's going to use that to adjust that weight, which means that this 3 is going to, at the end of this, is going to end up with a list of 5 different deltas, because 5 different neurons passed back a delta to it. And so what you do with this, it's getting a little crazy here, but you're just going to take this and average that together, and now you have a new delta here to pass back to its previous weights. So it can get kind of crazy in here, but what we're really doing, so we're taking our inputs, and we kind of pass it through, and it just jumps through the hoops here, applies all these weights. We get a result, and we figure out our delta, and then that delta starts passing back through each weight to each neuron, and it goes all the way back. So we're passing all the way back, And we just kind of keep doing that in order to adjust all those weights over time, and it kind of massages it in a way for our error rate to go down and things to get better on the network. But we do have a little bit of a problem here. We were doing this with just a single movie, and that actually introduces something called overfitting, because if we just run Star Wars through here a whole bunch of times, get our error rate down, that's not going to help us predict any other movies. That's going to be very exclusive to telling us whether or not we liked the Star Wars movie. And it's another example of overfitting. Like if you had image detection and you fed it like a whole bunch of pictures and said, these are apples and these are not, and all the pictures you had of apples were red apples, it's not going to do very good if you give it a picture of a green apple. It's going to say, no, it's not an apple, because your network is overfitted to your data. So you want to make sure that your data is very diverse, that you have kind of a wide range of data. I know you're giving me a look. I'm just a few minutes. I'm wrapping up. All right, so to do that, we're going to take a big old list of movies, movies that I've seen, so I have knowledge of whether or not I liked them, and then we can take all this other input value and pipe it in there. And don't look at those numbers; those are all made up. All right, so we're going to take our first movie. We'll take Star Wars, we'll pipe it through, go all the way to the end, and then we're just going to say, okay, the delta for that was 3.2. And then we're going to take a new movie, pipe that data in. All right, delta of that is 0.6. So we're going to go through our whole list of all of our movies and just keep tracking it through and saving what our delta value was. And once we've gone through all of our data, like, okay, we have a huge list of deltas. How are we going to adjust the weights so it's going to affect all these? Well, we just average it. We just average it, and this seems like maybe this wouldn't work, but it actually does. Like we just kind of take our lump sum of how much to nudge everything, and we can average it together, and that will make the slight adjustments. And over time, as we do this, our network will improve and find these patterns. So we take that delta, again, we pass it back, and then we take all of our movies and run them through again. And we keep doing that to lower our error rate. And sometimes you might have data that's just like insane amount of data. Like this is going to take forever just to run one pass. And so you can do different things like batching, where you're like, okay, we're just going to run 100 movies through, adjust the weights, and then take another 100 movies through and kind of keep doing it that way if you want. So now that we have our network, so say we've done this, we've run thousands of movies through, and we got our error rate really low, we now have our magic black box that we can throw new movies into, and it will tell us whether or not we're going to like the movie. And this is what's making predictions with unknown data. It's called like testing the network. We want to make sure that it works. So we're going to take a bunch of movies that I haven't seen, and we're going to throw it through our black box neural network and see what it suggests. And then we can just sort it based on what the prediction is per movie. And so I can see like, okay, so here's a list of movies, and all those are really great, really high prediction values, so it's likely that I'm going to like these movies. And hey, look, M. Night slipped in there, number 3, Split, so maybe I should finally forgive M. Night and go see the movie Split. And you can also take these results and find out which movies maybe I'm not going to like. And this looks like a pretty accurate list to me. All right, so that's it. So we did it. That's how we build kind of a basic neural network and how we can teach that network to have experience and learn from that experience by figuring out what an error rate is and figuring out like, okay, so I know that was bad. How can I improve? How can I get my error rate down? And if you think about this, like our network was tiny compared to what most machine learning is. Like if you think of like how does image recognition work? Well, take every pixel value, and that's an input. So you're going to take a picture, and you got thousands of input values, and then your hidden layers can start to find like edges in those values, and then maybe those edges can find shapes, and then eventually at one hidden layer is like, oh, I found a mouth based on what these other hidden layers are passing in, and maybe you have an output that says, does this picture have a face or not? And through all that data, it can collect and figure out that yes, it does. All right, so that is the end. I'm getting the look, but real quick, here's some additional resources. There's a fantastic book called Grokking Deep Learning. It's still in beta right now by Andrew W. Trask. And this is great. It doesn't require you knowing calculus. It does use Python, but I don't know any Python, and I could follow it pretty easily. There's also a deep learning video series on YouTube by 3 Blue 1 Brown, and this is fantastic. It's like 3 20-minute videos, and they're awesome. There's a couple of great talks. There's Erlang and Deep Learning by Garrett Smith from a couple of years ago at Erlang User Conference. Carmen Blake gave her talk building a neural network from scratch, and he goes through the process of eventually using Elixir processes to build his neural network, which is really fascinating. There's a great site by R2D3 called the Visual Introduction to Machine Learning. This doesn't do any math or formulas, but it gives you a great overview of what machine learning is getting for you. And then there's a couple of great courses. I haven't finished Andrew Ng's, but one day I will go back and hopefully understand it. And last thing, this site is awesome, playground.tensorflow.org. Go check it out, and that's it. Thanks.